Newton's third law tells us that for every action force, there's an equal but opposite reaction force. The official definition is if body A exerts a force on body B, then body B simultaneously exerts an oppositely directed force of equal magnitude on A. It's quite a lot of words. I prefer for every action force, there's an equal but opposite reaction force. Now, there's a lot of important stuff. If you are on ice skates and you pushed against a barrier, you would slip out and you'd fall on your face. That's because the barrier pushes you backwards. And the barrier only pushes you backwards because you pushed forwards on the barrier. So what happens is you have an action force. The ice skaters push forward on a barrier. Put a barrier in there. And that barrier force ice skaters onto barrier. The barrier exerts an equal but opposite force onto ice skaters. So you need to realize a number of things. Firstly, these two forces are equal to each other. The second thing is they are acting on two different objects. One acts on the barrier, one acts on the ice skaters. Sometimes action-reaction pairs will be contact forces. In this case, it's a contact force. They're in contact with each other. Another action-reaction pair is weight. So, for example, there's this ball and it's in the air. It is being attracted down to the earth. And strange but true, the earth is being attracted back up to the ball. So how does that work? Well, why isn't the earth bouncing up to the ball? The ball is moving quite clearly towards the earth. This is an action-reaction pair. Force on ball, equal but opposite force on earth. They are not in contact with each other, and therefore it is a non-contact force. But the earth, if I only apply a 2 Newton force to the earth's not going to move. 2 newtons on the stone, however, does make the stone move. So let's read very carefully. Newton's third law applies to contact forces and non-contact forces. And that is forces through a field. And remember, we've learned about gravitational fields, we've learned about electrostatic fields, we've learned about magnetic fields. I just want to show you this little video clip. It's very short. And what's happening here is there's a fire extinguisher. It's going to push out gases. Yet, this guy's on like a little wheelchair thing. The wheelchair is going to move forwards. So the gases go backwards, and yet the wheelchair moves forwards. How does that happen? These gases give a force against the air particles towards the right. The air particles in turn push the person forward on the wheels. That is the principle on which a rocket works as well, is that if you have a rocket, the gases all come out, and as those gases come out, they push a downward force, and it's a big downward force, and the platform then gives an equal but opposite force upwards to propel that rocket forwards. All forces in nature will occur in pairs, action-reaction pairs. You get an action force and a reaction force. The reaction force can't exist without the action force. They always act on different objects. They always have equal magnitude. They always have opposite directions. They're always along the same line. In other words, if the one is acting to the right, the other one is acting to the left. If the one is acting up, the other one is acting down. And they always occur at exactly the same time. Because they are acting on different objects, they can have different results depending on the mass of the object, how much friction there is with the object, etc. But it's important to consider each object separately. So, we've got this parachutist. He's in free fall. He has a mass of 100 kilograms, which means his weight is 980 newtons. And he is being attracted to the earth by 980 newtons, and he is attracting the earth with 980 newtons. The earth is huge, so it does not actually move, but the man moves towards the earth. The rate of acceleration, 9,8 meters per second. Action pair. Here I am, not me, but a person is pushing a car. The car experiences a forward force, but this person's hands get very sore because the car exerts a backward force on the person. A similar thing happens, somebody's wearing high heels and they are exerting a force down on the ground. So pressure, small little area, the ground exerts a force back onto the foot, and therefore the person's foot starts to get sore. So let's go back to this man and his vintage car. Man pushes a vintage car with a force of 400 newtons. If this is the action force, give the size and direction of the reaction force. 400 newtons to the right, the reaction force, 400 newtons to the left. On what object does the reaction force act? On the man. The man pushes car, car pushes man. If the maximum friction of the car is 300 newtons, will it accelerate? Now you might think, well, there's 400 newtons forward and 400 newtons back, so this car is not moving at all. Remember, you are only interested in the forces on the car. There's a 400 newton force forwards on the car. There's a 300 newton force backwards on the car. And therefore, will this car move? Yes, there's still 100 newtons acting in the forward direction. 400 minus 300. This 400 force over here is acting on the man, not on the car. So it has nothing to do with that relationship. What prevents the man, I mean, he's being pushed backwards now with 400 newtons. Why isn't he just flying backwards? Pew! Because he is in contact with the ground and there will be a frictional force that is balancing him. Different set of forces on man, different set of forces on car. So here we have the donkey pulls forward on the cart. The cart pulls backwards on the donkey. That's why the donkey starts to get tired. He keeps getting pulled backwards. I have got the weight of the book going towards the earth. The book is attracting the earth with exactly the same force. There is a force of the book onto the table. At the same time, the table is pushing the book upwards. Notice in every action-reaction pair that you have got equal forces. They are in opposite directions. They are along the same straight line. And they act on different objects.